Okay, and fine. And I will just share the ice cry. Okay, so the plan of this class is something like this. I'm going to, hopefully, all of you have had a look at all the hydrogen atom, the important formula and points that I send across to you, because we'll be using some of that in trying to solve problems today. And as I told you, I wanted to do angular momentum alongside. All right. So, what I will do right now, since I didn't have a sheet prepared for angular momentum, I'll run over a few of the important points that we need to remember to tackle angular momentum problems. And then go ahead, we will do hydrogen atom and angular momentum problems seamlessly. Okay. So, this is the basic idea. So, let me just start off by writing down the points that you need to remember to solve angular momentum problems. So, angular momentum. Okay, and let me put it so I hope this is visible. Okay, so important points and formulae. Okay, so hopefully this itself will serve as a sheet on which you can kind of try and recall important things. So the first, of course, is we will start off with orbital angular momentum, and the very important thing to remember are the commutation rules, if you remember. Okay, so the commutation rules, how does it go? One is L cross L is equal to IH cross L. And what does this stands for? Three different commutation laws, which is essentially Lx Ly commutation is equal to IH cross Ly. And then, of course, in cyclic order, Ly Lz commutation is IH cross Lx. And similarly, uh, Lz Lx is IH cross Ly. And what essentially it tells you that the three quantities can never be measured simultaneously. The other commutation law that is extremely important to remember is that your L square L is equal to 0. So L square, which is essentially a representation of the magnitude of the angular momentum, and it commutes with each and every component separately. Okay, so this is 0, this is also 0, this commutation, and as is this. Okay, so obviously only two components can be measured. The magnitude along with one component can be measured simultaneously, and usually the choice is made of L square and Lz, right? And if I kind of mentioned this last time when we were talking about your hydrogen atom, and of course in AMO and all you would have already done this again. The simultaneous eigenfunctions are your spherical harmonics, which usually you write it as ylm theta phi. Okay, so these are pure angular operators. If you remember the orbital angular momentum operators, they are pure angular operators, and the simultaneous So how does one write the eigenvalue equations? Again, something that you should remember. Okay, this is nothing but L into L plus 1 h cross square ylm theta phi. Sometimes please remember the L and the M are written as subscripts itself, one beside the other. L leading followed by M. And then of course you have an LZ YLM theta phi, which is equal to your MH cross YLM theta phi. A few pointers over here. Remember that your L should be greater than or equal to M square. Okay, and this is simply to do with the fact that the Z component, sorry, did I write this right? No, L square, right? So, yeah. So essentially, this is to do with the fact that the Z component itself cannot be greater in length than the length of the vector. All right. So this is the thing that one has to remember. So thereby M can take 2L plus 1 values And how does it range? It basically can go from minus L plus 1 all the way to L minus 1 L. So it can take essentially 2 L plus 1 values. Okay. So this is an important thing to remember. And in the case of the orbital angular momentum, what we have to remember is that your L takes on values which are essentially, it can start from 0, 1, 2, and so on and so forth. Okay. So obviously, yeah, so this is basically thing for orbital angular momentum. So now let me just look at, because I was just looking at what all you need to remember. Now, the next thing that we need to remember is what is the form of the eigenfunctions. If you, for over here itself, I will do Lz eigenfunctions have the form. So if you remember something like this itself, it's good. Okay. Yeah, it has the form. So, and of course it's a, there's a root 2 pi which goes ahead of it, or root of 1 upon root 2 pi, okay, which goes ahead of it. But that anyway, it's something you can always get by normalization. This is important. Okay. Similarly, L square eigenfunctions have the form. So the key thing, apart from all the other constants which are there, is basically it will have PLM of cos theta. So this is the associated Legendre polynomial. Okay. Lm being the, what do you call it, L being the degree and m being the number of times it's differentiated. Okay. And of course it's a function of cos theta. Right. So this much if you remember, at least it will take you a long way. All right. Next, after we kind of have learned the more or less the idea of the angular momentum of the, what do you call it, the orbital angular momentum, let us now head to total general angular momentum. Okay, so general angular momentum, okay, which basically discusses orbital angular momentum and also other kinds of angular momentum. So what are the rules here? So the key rules are essentially again your commutation laws, which of course I will just write them down now as J cross J is equal to IH cross J, and of course your J square J equal to 0. All right. Then we write it as if Jm, okay, is a common eigenfunction function of J square and Jz in line with what we did for orbital angular momentum. Then remember that J square operating on Jm will again give you J into J plus 1 H cross square Jm. And similarly, Jz operating on Jm will give you mh cross Jm, right? So you start off on this premise, and then of course there is a lot of interesting things that happen, and very key amongst the treatment of general angular momentum, which can of course be applied to orbital angular momentum as well as spin separately. But nonetheless, important thing is that you remember these two ladder operators and how they are defined. Okay, because a lot of questions usually sometimes come with these ladder operators. Okay. And very, very important is that these are, of course, not Hermitian operators. Okay. So they are not observable. So, right, by any stretch of imagination. So, what I will write over here is trivial, but nonetheless, it's important to remember. Okay. So, they're non Hermitian. I mean, they're pretty much like the A and A dagger or A plus and A minus of the simple harmonic oscillator. Non-Hermitian, not observables. Okay, very important to remember. Right. So now let's just continue with our preparation sheet, so to speak. Okay, for doing all the angular momentum problems. So right. So now what is the modus operandi of the J plus and J minus? What you have to remember is that, so let me just put it down. Uh, yeah, the commutator between J plus and J minus is essentially some 2 h cross Jz, and just below it I will just write down your J plus J minus actually looks like this. It's J square minus Jz square plus h cross Jz. You can remember it, it will help instead of having to work it out. And similarly your J minus J plus looks like this. It's essentially J square minus Jz square. Okay, and then you have a minus h cross Jz. Okay, so this is good. Then of course, what you also will realize is that if I did, just hang on a second, if I did J square commutation with either J plus or J minus, considering that they are made up of Jx and Jy, this will always be 0. Not the case with Jz and J plus, in which case you get, let me just write it down, you get a h cross J plus, and similarly a Jz and J minus will give you a minus h cross J minus. Okay, so this is kind of important, these things to remember. So what it essentially tells you, that if you basically operated J square on J plus of Jm, J plus or J minus for that matter, let me not bother with this, you would still get J into J plus 1 h cross square J plus J or J minus of Jm. So essentially it tells you that J plus and J minus do not do anything to the magnitude of the angular momentum. On the other hand, if you actually did Jz on J plus of Jm, what you would end up getting is m plus 1 h cross, okay, J plus of Jm. So essentially it tells you that J plus of Jm is an eigenfunction of Jz, but it now has an eigenvalue of m plus 1 h cross. So which means that the magnitude of the Jz component has gone up by h cross. Okay. Similarly, if you did Jz of J minus Jm, you would get essentially m minus 1 h cross J minus Jm. So what it actually tells you is that your, again, over here we know your m square has to be less than J square, all right? But what basically you come to the conclusion over here, there is a whole bunch of derivations that we did last, in your first semester. We need not go through that. Your J can essentially take on values of 0, half, 1, 3 by 2, 2, and so on and so forth. Okay, and your m in each case can again take on 2j plus 1 values, okay, which essentially goes from minus j plus 1 all the way to j minus 1 j. Okay, so this is essentially the whole thing. And obviously the j values which are, so you have integral values, you have half integral values. So the ones which are half integral do not have complete contribution. So here I'm not specifying whether they are from a single source, they are from addition of angular momentum. But what you have to realize that the moment you have half integral values, it cannot be fully orbital angular momentum. Okay, it has to be also at least partially coming from a different source, and that is what you call as your spin angular momentum. Okay, or your intrinsic angular momentum. So this is the basic thing what I wanted you to remember about general angular momentum. Then beyond this, let's go on. Just one thing, I mean, it may help if you remember this, but I will not insist because sometimes you're asked to write matrix forms of various things. So if you can remember that your J plus acting on Jm essentially will give you J into J plus 1 minus M into M plus 1 to the power of half H cross, and then you have J M plus 1. So remember, it will of course be a non-diagonal matrix. Okay, so that's not a thing. I mean, because Jm is not really an eigen function of J plus. Similarly, J minus Jm will be J into J plus 1. Then I think it is minus M into M minus 1, if I'm not mistaken. Yep. Minus M into M minus 1 to the power of half H cross J M minus 1. Okay, so this is essentially the two things which may help you if you can remember how to go about doing the matrices. All right. What else do we really need over here? Let's just go to spin. All right, 1/2. Okay, so that's kind of important. So let's look at the special case of spin 1/2. So if you remember this, essentially it means your J is equal to half and your M can only take on values of plus half and minus half, right? So you have two possible states. So that can be half and half, or it can be half and minus half. Correct? These are your two states. And very often this is, people write it like this and this like this, or sometimes they write it as alpha beta. Let's just stick to this because I find that this is one of the most common ways in which people write it out. So what you have to remember over here is that okay, so let's just move on. What is very important over here is that if you try to, I mean, I don't think there's any difficulty in figuring out what would be S square of this or S square of this. This would be just, of course, both of them would be equal to half into half plus 1. So it will be 3 by 4 h cross square. And then, of course, since it's an eigenfunction, you will get the same thing. Okay. So this is one. The other is, of course, if you did an SZ of this, what would you get? You would get h cross by 2, same guy. And SZ of this, you would get an h cross by 2, the reverse. Okay, basically the same eigenfunction. So now let us just move on. And what is very important is when
for the SZ down vector, isn't that minus h cross by 2?
Yes, you're right. Yes. Sorry, my bad. Absolutely, you're right. Has it come, the minus? Yeah. Sometimes I'm not so lucky. It doesn't come in the same position once I tear off the page. Yeah, you're right. Thanks. Okay, so now let's go here. And so a very important thing is to figure out how your, so I'm not going to, so as you can imagine, if I tried to do an S plus of this, I would get a 0, correct? Yeah, sorry, yeah, an up vector, I would get a 0. If I tried to do the S plus of the down, okay, then I would end up getting H cross times the up. Okay, so this is a little important to remember. Similarly, if I did S minus of the up, I would get essentially H cross times the down, right? And if I did this, I would get the null vector. Okay, kind of important to remember these rules. It may help you solve problems faster. All right. Similarly, if I try to do an SX of the up, all right, I actually will end up getting h cross by 2 the down. So remember, the fact that your wave function itself is changing would mean that, of course, it's not an eigenfunction. Similarly, you can do an SX of the down, okay, and you'll end up getting h cross by 2 up, okay. And if you did sy of up, you would end up getting I h cross by 2 down, and sy of down would give me minus I h cross by 2 up. Okay, so this is basically a set of things that it's good to remember. What else would it be good to remember? Is that over here, remember, in the case of the spin half, this is a special case, and here you end up getting always your expectation value of sx square is equal to your expectation value of sy square is equal to your expectation value of sz square. If you remember, your s square expectation value would always be 3 by 4 h cross square. So this is going to be 1 by 4 h cross square each, because expectation value of s square, of course, is going to be expectation value of sx square plus expectation value of sy square plus expectation value of sz square. Okay, so this is another important thing to remember. What else very important about is that these anti-commute, right? So you can write it like this. Okay, and of course you can just continue with this. Okay, so they all anti-commute with each other. Yeah, I wrote the full form. What is the way to write this in so essentially sx sy plus is equal to 0. Similarly, sy sz plus is equal to 0. Order is of course not important here, and sz sx plus is equal to 0, right? Now, if you combine the commutation and the anti-commutation laws, you get something interesting. Essentially, you will get what I always write as Sj Sk is equal to IH cross by 2 SL, where J, K, L are X, Y, Z in cyclic order. All right. So, right. So this is a very important thing again. What else would be an important thing to remember is basically you can remember the matrix forms. I mean, if you can, it's will help. I'm not putting it down over here. The other thing is that the link with the poly spin matrices, right? So essentially what you need to remember is that S is nothing but H cross by 2 sigma, or your sigma is equal to 2 by H cross S, right? And you can essentially write down all the rules that you saw in terms of the what do you call it, the polyspin matrices. So for instance, you can write your sigma x sigma y commutation will become essentially 2i sigma z. Similarly, sigma y sigma z is 2i sigma x. Similarly, sigma z sigma x commutation is 2i sigma y. Okay, right. What about anti-commutation? Please remember, of course, they anti-commute. Okay, so quite important. Just like the spin matrices. operators rather. Yeah, this they anti-commute. And what else? Very important, if you square them, you're going to get 1. Okay, all of them. So try and remember this. It is something which I think comes in handy quite often. All right. Anything else? Yeah. So from the commutation and the anti-commutation, you can also write your sigma I, sigma j is equal to I, sigma k, where, okay, I should actually write it as j, this I should write as k, and this I'm going to write as L, because, don't want any confusion with the I as in the square root of -1. Okay, is x, y, z in cyclic order. All right, so I think we can stop here. All right, they can just continue on and on. All right, maybe one last thing, which is essentially to do with the addition of angular momentum. Okay, that is important. So let us just look at the rules with respect to addition of angular momentum. And so remember, when you are trying to add to angular momentum, remember that they have to be independent of each other. Okay, so essentially, let us imagine. So let's go for addition of angular momentum. Okay, so if you have essentially one angular momentum and the other angular momentum, remember what is very important. All the rules that we talk about are essentially if these two are independent sources. Okay, they have independent sources, which means what? Which essentially means that your J1 will completely commute with J2. Okay, yeah, each and every component of J1 commutes with each and every component of J2. Okay, so given that, okay, let us now see what is going to be the situation for J equal to J1 plus J2. Okay, now what you have to remember is that you can write down the uh, so of course this J will have, okay, so let me just now say, so the combined system can be represented in two ways. Can be, when I say represented, I'm talking about the basis sets, okay, in two ways. Okay, so what are the two ways which we can talk about? The first one is that you, of course, can write it down in terms of J1 square, J1z, okay, which is a common eigenfunction of J1 square and J1z, and J2 square and J2z. Okay, so we can use the common eigenfunctions of these, just direct product, common eigenfunctions of these. Okay, so the common eigenfunctions of these four can be written. So essentially your total thing can be written as J1, sorry, my bad, J1 M1 and J2 M2. Okay, so which can be written as essentially J1, J2, M1, M2. Okay, so this is one way in which you can write the common eigenfunctions. How many of these will be there? Then that will be essentially 2J1 plus 1 into 2J2 plus 1 will be the total number of independent. When I mean say independent, I mean linearly independent. Okay, independent eigenfunctions. The other way of doing it would be to take J square, J1 square, J2 square and Jz. Okay, so this is another way of doing it. And how will we write down this whole thing? it will be essentially J. Have we lost connection? Am I audible?
You're back now.
Okay. Yeah, because I saw my video had completely frozen. Okay, so I'm hoping that you have heard that, there are two ways of representing the combined system. And one is by using common eigenfunctions of J1 square, J1z, J2 square, J2z. How many linearly independent eigenfunctions you will have over here? It will be 2J1 plus 1 into 2J2 plus 1, right? What is the other case? You can go from you can use common eigenfunctions of J square, not yeah J1 square, J2 square, and Jz. Okay, and essentially you can write down the common eigenfunction like I've shown over here. All right, and again, of course, you will have 2J1 plus 1 into 2J2 plus 1 common, what do you call, linearly, so linearly independent eigenfunctions. Okay, and what you have to remember is that you can go from essentially this system, right? Your J1, J2, M1, M2 representation to, you can go to your J1, J2, M, okay, representation. How? Basically, you can do it by a unitary transformation. Okay, a unitary transformation. And remember that basically you can write down the expansion. So just give me a second. I have a, so you can write down your eigenfunction here, which is your J M J1 J2 can be written as summation over all of M1 and M2. All right, and you have essentially this particular thing, your J1 J2 M1 M2 inner product with JM J1 J2. And then of course here you will have the wave function. What is it? Your J1 J2 M1 M2. Sorry, it had to go into the next line, right? And these guys here, are essentially your Clebsch-Gordon coefficients. Okay, so this is something, I mean, just keep this definition in mind. If you can remember some of the Clebsch-Gordon coefficients, well and good. What is the link between your J and your J1, J2? Remember, your J can take values from J1 plus J2. Then it can, of course, go to J1 plus J2 minus 1 all the way to J1 minus J2. All right, sorry, modulus. All right, and for each of these, of course, the M values can go from minus J plus 1 all the way to J. Okay, so this is an important thing to remember. And I think what it would help if you kept the specific case of the spin half in mind. So when we basically add up to spin halves, I'm sure that you have done this now as a part of AMO course, but that was in your third semester. So let's just kind of repeat it once. So I'm going to scan these sheets, okay, and send it off to your juniors as what to remember about angular momentum, so they don't need to take notes when I'm doing it. All right, so let's just look at the special case of addition of two spin halves. Okay, and what is the basic situation over here? You can of course now go for the common eigenfunctions. So let me write it down properly. Yeah, common eigenfunctions of, so here I can write it as S1 square, S1Z, S2 square, S2Z. And what will this be actually? It will be both up, up, okay? Or it can be first one up, second one down. Or it can be first one down, second one up, or it could be both down, down. Correct? So this is the common eigenfunctions of S1 square, S1Z, S2 square, S2Z. You could write it as J1 square, J1Z, J2 square, J2Z if you wish, no problems. Just remember over here, your J1 is equal to half and your J2 is also equal to half. Okay, so this is why either you can do that or you can use the common eigenfunctions of J, or let's put it as S square, SZ, S1 square, S2 square. And what is this over here? Please remember that your S value can go from S1 plus S2. Okay, so that will be essentially half plus half. Okay, I should have written, so you can write it as S1 or you can write it as J1. You can write it as S2 or J2, okay, which is equal to 1. And the other value it can take is modulus of S1 minus S2. There's no other value possible because you have to keep a difference of 1. And that is going to be essentially half minus half, which is going to be 0. So your S value can be 1 or it can be 0. So in the case of the 0, all right, so please remember, so S being equal to 0, what is this called? This is called your singlet state, correct? I'm presuming either CGR ma'am or RD sir would have done it with you. All right. And what is the way it is written in terms of the other eigenfunctions? Essentially, you write it. So let me just give me a second. I'll just take it from the way it has been written in one of these books. I don't want to put in my own talka. Yeah, so you can write it as your chi 0, 0 is equal to 1 by root 2, and you can write it as essentially up, down, minus, down, up. And please remember, this is anti-symmetric, right? If you change the up and the down, it actually changes in sign, right? Then you can have the S is equal to 1, which is essentially your triplet state, okay? And your triplet state can have what? Your chi 1, you can have essentially 1, or you can have chi 1, 0, or you can have chi 1 minus 1, right? Those are all your total M values. And this will be essentially, there's only one way of doing it, which is this. Similarly, here also, there is only one way of doing this, which is both down. Here in between, you could have a 1 by root 2. And this is essentially up, down, plus, down, up. Okay. And remember, all these three states are symmetric. Okay. Change the up and down, and this is anti-symmetric. Okay. So this is, I think, if you can remember this much, already you're doing pretty good. Okay. So I will close it here now. All right. So now, fine. So after we have done this, let's start looking at some of the problems. I don't know how many we'll be able to solve today, but doesn't matter. I will run you through the solutions as well, and I will give you the problems that we are discussing as well as the solutions. Okay. So since a lot of people are not there, I think it is important that we perhaps function this way. Okay. So let me stop the share. And yeah, what I will share now. Yeah, so let me share my screen itself. All right. So let me just go here. Yeah, so there's whole bunches of problems as you can see. I will go for the hydrogen atom problems. Okay, is everybody able to see it? Yeah.
Yes, ma'am.
Okay, great. So we can just look at the first problem. What does it say? What is the degeneracy of the first excited state of an isolated hydrogen atom? All right. So this is the very first question that has been asked. So let me just go here, and I have the solutions over here. I may have run off to a different page. Let me just go right at the top. Okay. So is everybody able to see my handwritten stuff now? Yeah.
Yes, ma'am.
Okay. So now, so the way of, I think this is going to be a fairly trivial problem. It's a matter of, as I say, just looking at it. So just look at it over here. The first excited state of an isolated hydrogen atom will have principal quantum number 2. Yeah, that is quite evident. So what can be the values of L? L can take values of 0 and 1. When it takes a value of 0, how many M values are possible? 1. When it takes L is 1, how many M values are possible? +1, 0, and -1. So total of 4. So your degeneracy will be 4. You could have also just done n square. Okay, so please remember that you have what do you call? I think I have written it down in that points to remember, but I'm not very sure of it. I've recently also taught this to your juniors, so I don't know where exactly I wrote this. You could just do n square. All right, yeah, and that would give you the degeneracy of a state.
Ma'am, what about spin?
Sorry. So the point is over here, I mean, you're talking about spin, in which case, but here you're talking about degeneracy in the sense how many, see spin, let's look at it this way, Nitin. Okay, let's just go with how do you define degeneracy? So let's start off with that. How would you define degeneracy?
Something which has same energy.
Exactly. Yeah. So you say what has same energy. Now the point is that and what has same energy? You are talking about linearly independent wave functions, correct? Am I right? Yes. So here the point is that unless and until you put in the spin by hand, the up and the down, you actually wouldn't be looking for that as an answer. So you would go to say that there are 4. So how do we write the hydrogen atom wave function? Okay, just think about it. You're writing it with the radial function and the spherical harmonic. We have not yet put in the spin. Okay, correct? Yes. So the point is that since they are asking you with the hydrogen atom, you should basically go without the spin. Okay, so this is my logic to the whole thing. All right, that so in that sense, if you think about it, it's probably a bit ambiguous, because if you did put the spin wave function by hand, okay, then of course you're going to say that there are more linearly independent guys. But actually when you think about a hydrogen atom wave function, any book you pick up, okay, they will only talk about the radial part and the spherical harmonic part. Now imagine that that is what you're being asked. How many of these linearly independent guys are going to give you the same energy when you have a principal quantum number of 2? And actually the answer will be 4 then. Okay. So as I say, the spin is something which, first of all, you will have to put in by hand as an extra realization that it also has an intrinsic angular momentum. And of course, then bring in Pauli's exclusion principle and say there are only 2 electrons and so on and so forth. Okay, but over here, when you're talking about isolated hydrogen atom, I think it is best to ignore that factor. At least, this is the solutions I've seen in zillion million places. This is what they expect. Hydrogen atom, they are essentially talking about the radial function into the spherical harmonic, and all the questions essentially link up with that. Nobody will take the spin wave function and also put it in. Essentially also because you cannot really calculate much there, right? Probabilities and so forth, you cannot. It's an intrinsic angular momentum. We do not know what form it has, right? Anyway, I mean,
Yes,
so this is my take on the whole business. Okay, if you have
yes,
any
ma'am.
thoughts
I
on.
too agree with what you said, ma'am, but we've been taught that degeneracy of an n state is 2n square, including spin. So that's why I asked, ma'am.
Fine. See, look at the solution. See, for instance, let's just check out the available solutions away. See, if there is a confusion, okay, then I would suggest the best thing you can do. I don't think it's this one. It's this one. Okay, so can you see the problem again? Okay, so of course I here
Yes, ma'am.
unluckily enough you also have 8 as the solution. Okay, so the okay, let me just ask ARU's opinion also on this. Okay, yeah, what she has seen. But most of the time, what I find is that people generally talk about just the radial and the this thing. See, if they had asked you the number of electrons, okay, then I agree that you don't have a choice there, right? However, if they just ask you for the what do you call degeneracy, I'm not sure how it works. All right. So because there are, frankly speaking, only 4 radial functions which are essentially linearly independent and show up with the same energy. So how it works, I really don't know. Okay. I will just inquire with her. It's a valid point, Nitin. Okay. And I do not deny that there should be confusion. But I have been working under this assumption. But better to, I think, ask another source and just, see what she says. Okay. And I'll get back to you on this. All right.
Okay.
Fine. So now let's have a look at the second problem. And this is essentially what you have been given is a wave function which is described in theta phi, all right? And it is 1 by root 30 phi y40 plus y60 minus 2 y63, all right? Where this ylm theta phi are the spherical harmonics. Okay, so obviously what you realize is that the bottom one is essentially giving you the L state and the top one is giving you the M state. All right, and this is essentially nothing but a linear what do you call it, combination, all right, of 3 different spherical harmonics. Now what they have said is what is the probability of finding the system in a state with M is equal to 0. All right, now, obviously, it will be this guy, which will give you an M is equal to 0. It will return a M is equal to 0, as well as this. And how would you find the probability? Essentially, it will have to do with the coefficient of this plus the coefficient of this, or actually not just the coefficient of this. It will be this square divided by root 30 plus this square divided by root 30. And you can calculate the probability like that. So let me just see what I have done in the solution. Okay, so let me just go to 100%. Okay, see, I'm doing this for the purpose of time. I would have loved to have solved it out. I know it's easier that way, but as we really have a paucity of time now. Okay, so let me just go to my annotate button. Spotlight, yeah. So yeah, so what is good to do in always in such a case is before you come to any conclusion, just make sure the thing is normalized. Okay, yeah, otherwise please remember you should take the inner product of this guy. Oh, sorry about that, I just went up too much. Yeah, so otherwise you should take the wave function, basically the inner product of the wave function with itself, and divide by that. Okay, so it is always a good idea to first make sure that the wave function is normalized. So this is what one is doing over here, finding out what is this inner product of psi with itself. And remember that the spherical harmonics are all orthogonal to each other. If L doesn't match or M doesn't match, the inner products are going to give you 0. Okay, otherwise it should give you 1. So using that, you realize that the thing is actually normalized. Okay, so remember again, anytime, okay, this is a common way in people catch you off guard. Okay, make sure that the wave function is normalized. All right, now once you have done that, okay, you want the probability of when m is equal to 0. So essentially it is going to be these two, right? The first one, the first term over here, okay, this and this term. Okay, so you will get a 25 by 30 coming from here, and you'll have a 1 by 30 coming from here. So you should get an answer of 26 by 30, which can be, of course, simplified to 13 by 15. All right, so let's have go back and look at the problems again. So that's essentially, you have a 13 by 15, that is choice D. All right, I will send these problems to you today itself. Okay, no matter how many we actually run through in class, they're going to be with you. I should have done that earlier, but I didn't. Never too late to start rectifying things. All right, now let's go to the third problem. I think we'll just be able to do one more problem and stop. Okay, and what is this? This essentially gives you the ground state wave function of a hydrogen atom. And I had asked you to try and remember this form, right? This e to the power of minus r by a, where you should remember that your a is nothing but your modified Bohr radius, right? Okay. So now, so it's given where a is a constant. Now, if PR dr is the probability of finding the electron between r and r plus dr, then, okay, so let us see what all are given over here. Your PR is equal to 0 at r equal to 0. Your PR is max at r equal to 0. Your PR is maximum at r equal to a. And integral 0 to infinity PR dr must be equal to 1. Now, let us just look at what looks likely over here. PR being maximum at r equal to 0 is of course going to be false, right? Because then it means that the electron should be at r equal to 0 with maximum probability. Electron being at r equal to 0 essentially means that the electron is sitting inside your proton, correct? Your hydrogen atom proton, which means essentially the atom doesn't exist. Okay, there's going to be an annihilation, right? I mean, it's a positive charge, a negative charge, right? So the point is that stability of matter should basically make you discard. Okay, PR is maximum at r equal to 0. This looks very likely that it's maximum at r equal to a. The D is definitely true because yes, if it's a bound system and this is a bound, sorry about that. Okay, so this is 3 that we are looking at. This is a bound state wave function. So given that, you know, the electron is somewhere around the nucleus, and thereby if you take a probability, this is the entire range of r, 0 to infinity, you're going to get a 1. So this is definitely true. It looks like C could be true. B is definitely not true, and it's likely that A is also true. So it looks like that, you know, so maybe one should say that which of the following statements is false. So obviously the one that is false is B. Okay, the others look like they are true, but you can of course go ahead and solve it out. Okay, so let me just share my solution with you. Okay, so this is what it is, I think. Okay, so in the hydrogen, all right, so I have written certain formula from here, all right, let's not worry about it. I've just tried to justify what is the ground state, all right, and then what I have done over here is essentially written out PR dr, okay, and what you see that there is an r square factor multiplying your psi star, okay, dr, okay. So the point is that that r square factor, okay, will ensure that this guy actually goes to 0 at r equal to 0. So which basically tells you that option A is correct. Now what you have over here is again the r square rr, which is nothing but your PR over here, and as a function of r. And what you do notice is that you have a maximum. Actually, it should be r by a over here. It has a maximum at 1. Okay. So please remember that's the most likely radius, right? The Bohr radius or the modified Bohr radius. So thereby the probability of finding the electron at that particular radius is going to be maximum. Okay, so there's nothing surprising about it. And then of course, if you wish, you can carry out this integration, right, which I have done, and then you can prove it to be equal to 1. But frankly, you don't need all these shenanigans. Okay, you don't need to do all these calculations. Just, going by sheer what you know about the hydrogen atom, I think you can work this particular answer out. So essentially, I need to reframe the question a bit, that which of the following statements is false. So patently, of course, the statement B is false, that your PR is maximum at r equal to 0. The rest of the three statements are all true. Okay. All right. So I think we have gone over the time limit. What I will do now is I will stop the share, stop the recording. I will send you my class notes, of course, which will help you to basically have a kind of a sheet which you can revise to do angular momentum problems. And in the next class, whenever that is, we will run through the rest of the hydrogen atom problems as well as the angular momentum problems. In the meantime, I will also send you problems, extra problems on hydrogen atom, which you can start looking at. Okay. Fine. So I'm sorry it was a rushed class because, yeah, I think we did do the, like the things, points you need to remember about angular momentum a little carefully. But I'd like to have time at least to discuss a whole bunch of problems. Okay. So fine then, I'll stop the recording here.